Okay, the subject of this presentation, which covers slides 53, 54, and 55 in the version of the PowerPoint dated December 14th, 2015, are different formats for plotting binding curves. And so we're going to treat what kind of information comes out of these plots, which of course indicates why you would want to do it, and will help you therefore know whether you would like to use these in formats in analyzing your own data, and then of course also understanding data presented in this format in journal articles. So the first two slides cover something called the Hill plot and the Scatchard plot. These plots are both designed to look at cooperativity. One limitation of both of them is that you do need to plot, that both plots require use of LF or free ligand. These are not plots in total ligand, but rather plots in free ligand. If that's not something you measure directly from the experiment, you need to basically do some preliminary analyses to infer what the free ligand concentration is, and if necessary, iterate those estimates before you get to the final analysis. But anyway, if you do have free ligand concentration numbers available, the Hill plot is a very powerful way to estimate what the degree of cooperativity is in a binding experiment. And so the Hill plot basically estimates the cooperativity. It is what's called a linearized form. It takes the binding curve and reorganizes the data in a way that it should give you a straight line. And the critical point of the Hill plot is that the slope of that straight line gives you a direct experimental estimate of n. You do need to know the level at full saturation for this plot to be effective, and I'll come back to that at the end. The key of course, underlying chemical and mathematical equations describing a cooperative binding equilibrium are described up top. We've seen them, of course, many times. What the Hill plot does is reorganize this in a way that you get a linear relationship once you take the proper logarithms of different parameters. And so the math here is described in the next line. So simply taking the SRLN and SRF terms over here and multiplying through by the reciprocal of those terms, you end up getting on the left side of the equation this expression. On the left side of the equation, you end up with this expression, right? So that's one, and then so you divide through basically by KD over N. That comes down here in the denominator. You multiply through by the reciprocal of SRLN over SRF. Those terms, therefore, are removed from the right side of the equation, and the reciprocal of them moves over to the left side of the equation. So simply doing this rather trivial algebraic rearrangement and then taking the logarithm gives you essentially the Hill plot. And so what you get is the logarithm of SRLN, the concentration of bound receptor, over SRF, the concentration of free receptor, is going to be equal to the logarithm of LF to the N over KD to the N. And of course, this ratio here is effectively LF over KD, that ratio to the nth power, and the logarithm of something to the nth power is N times logarithm of the ratio, and when you take the logarithm of a ratio, it is equivalent to the difference between the logarithm of the numerator and the denominator. So this is a rather trivial algebraic expansion that is really one step away from the fundamental mathematical equation describing a cooperative equilibrium binding. So this is effectively the Hill plot, the ratio of the ratio bound receptor over free receptor at different points in the titration will be equivalent to N, the degree of kinetic cooperativity, times the logarithm of the free ligand concentration minus N times the logarithm of KD. So one very simple reference point here is what happens when log LF is equal to log KD. Right? We all know that when LF is equal to KD, the reaction should be at 50% saturation. Of course, these two terms cancel at that point, and that means that that means the logarithm of the concentration ratio, the ratio of bound to free conceptor, the logarithm is 0. Of course, the logarithm is 0 when the argument of the logarithm is equal to 1. And so that says that at the point when log LF equals log KD, or when LF equals KD, basically you have an equal amount of bound and free receptor, so those two numbers are equal. That gives you 1. Of course, logarithm of 1 is 0, so when you have the logarithm of the ratio of bound to free is 0, that happens at a value of log KF equal to log KD. So we've been through this many times, and obviously that's a fundamental reference point for analysis of binding equilibria. The new information here is that the slope in this linear plot is now a direct measure of n. So let's think now about how we would get this value, basically the ratio of the bound to free receptor. And that's shown in the lower left here. And so if we have a idealized fractional saturation curve, if you think about it, the amount of bound receptor is proportional to the distance of the curve from the horizontal axis, whereas the free receptor, the concentration of the free receptor, is proportional to the distance of that curve from the 1.0 point, right? So when you start with nothing bound, right, the distance from the 1.0 point down to where the curve is, that's 1.0, right? In the fractional saturation scale, that means everything that means nothing is bound. There's 0 fractional saturation, all of the receptor is free. This distance is then proportional to the amount of free receptor. When you get towards the full saturation, of course, this distance here is proportional to the amount that's bound, and now this distance left here between the 1.0 line and the curve, that would be proportional to the amount free. So at any point in this curve, the ratio of the distance of the curve from the bottom, which is a measure of the amount bound, to the distance of the curve from the 1.0 point, which is a measure of the amount free, that ratio gives you an estimate of the ratio of those two distances is an estimate of the free to bound. And so basically, the Hill plot, we can convert log of concentration bound to concentration, log of bound receptor concentration to free receptor concentration. We can convert that based on this analysis to log of y bar, the distance proportional to the amount bound, over 1 minus y bar, the distance proportional to the amount free. And so we get log of y bar over 1 minus y bar is equal to n, the kinetic cooperativity, times log LF minus n times log KD. So this is, of course, very similar to what we saw here. We've just replotted this ratio of bound to free receptor in a form that's, let's say, more readily extractable in many cases from the data that you have. Now note that there is one trick here. To plot 1 minus y bar, we do need to know the saturation point. Of course, if we have data in fractional saturation, we know that fractional saturation maxes at 1. But if we're looking at some signal that is proportional to fractional saturation but on an arbitrary scale, we will really only know where we hit full fractional saturation if we know where the saturation point is. So in working with real data to do a Hill analysis, you will be, you need to know where full saturation is in order that you can calculate a parameter equivalent to 1 minus y bar. So experimentally, the full the saturation point needs to be defined. Now, there is a software module in Prism that actually will do a Hill plot for you, but it will, of course, ask you where in your coordinate system, in whatever parameter you're measuring that's proportional to saturation, it will ask you where the fully saturated value is, right? Because you need to know that to look at the ratio of the bound receptor to the free receptor. You need to know where full saturation is to get that ratio. So the Hill plot in the end, again, there are some limitations to it. You do need to know free ligand concentration. You also need to know where the full saturation point is, so you can calculate the bound to free ratio. But once you've done that and taken the logarithm of the bound to free ratio, or a parameter equivalent to that, like fractional saturation over 1 minus fractional saturation, you get a simple linear plot relative to log of free ligand in the slope, it gives you an excellent experimental estimate. Again, assuming you know the free ligand well and you know the full saturation point well, this gives you a direct estimate of the kinetic cooperativity, which is, of course, quite valuable. That's why people use Hill plots. Okay, the second plot relative to the analysis of cooperativity that's frequently seen in the literature is something called a Scatchard plot. A Scatchard plot is, rather than a way to measure cooperativity, the Scatchard plot is a way to test whether n is equal to 1, right? So it tests for independent site binding, so it basically is a way to see whether or not there is cooperativity. It also requires the use of LF. The bottom line of the Scatchard plot is that an independent site binding gives you a straight line, and a cooperative binding gives you a curved line. At some point in my career, I thought the Scatchard plot was sort of a historical artifact. You know, why bother doing this if you can do a Hill plot? But that actually was quite naive, because as I have done more and more analysis of binding equilibria in the work in my lab, I have learned that the Scatchard plot is in fact very sensitive to small degrees of cooperativity and is an excellent way to detect cooperativity. And so we'll now go through explaining that. So here's all the math. It's really pretty simple algebraically. I guess before we go through the math, let's look at where we're going to end up. Where we're going to end up is y bar over LF. So that's the ratio of fractional saturation. Of course, fractional saturation is proportional to bound receptor. So some people would describe the Scatchard plot as a plot of bound receptor divided by free ligand, bound receptor over free ligand versus bound receptor. Because bound receptor is proportional to y bar, we can plot it as y bar over free ligand versus y bar. Now this is a rather curious set of parameters, if you think about it. Of course, in the course of the binding experiment, y bar is going up in some way determined by the KD and the degree of cooperativity. And then y bar over LF, the bound receptor concentration or something proportional to that divided by free ligand. You know, these are not intuitively, it is not intuitively obvious why these parameters are interesting. But when we do the math, it will show that a non-cooperative binding gives you a straight line. And then after we go through that little algebraic exercise, I'll explain to you why the other plots are curved. And in that, I think will make it clear why this is really an excellent way to detect the presence of cooperativity. So once again, like we usually do in analyzing the math of binding equilibria, we start with the fundamental mathematical equation up here describing an equilibrium binding reaction. Again, we actually start with exactly the same. We then proceed with a similar rearrangement to what we did last time. But rather than multiplying through by bound receptor over free receptor, we multiply through by bound receptor over free ligand to the end. So we basically take these two terms, multiply by the reciprocal, and bring them over to this side of the equation. We divide through by the dissociation constant exactly the way that we did before, and we get the ratio of bound receptor over free ligand to the end is equal to the ratio of free receptor over KD to the end. Again, this is one step forward from simply the fundamental mathematical equation describing the cooperative binding equilibrium. Then we simply expand the free receptor based on conservation of mass into total receptor minus bound receptor. And we're now almost all the way there. To get from this kind of expression to fractional saturation, of course, we want to divide through by a total receptor. Because, right, if we, here we have SRLN in our equation. If we divide SRLN by SRT, we will go to fractional saturation, which is a more useful coordinate system for sort of to consider things, you know, in a conceptual way. And so let's go ahead and do that. We divide SRLN through by SRT over here, and that means also we have to divide this difference through by SRT. So we go ahead and do that and expand that, and we get SRLN over SRT, of course, is y bar over LF to the n. We now have exactly the vertical axis that we want, with the exception of the fact that this is describing the general case for cooperative binding. Over here, it's limited to n equals 1. The whole point of the Scatchard plot is to verify that n equals 1. So Now on this side, so we get y bar over LF to the nth power on the left. On the right, we get SRT divided by SRT. That's, of course, 1. And then we get minus SRLN over SRT. That's, once again, y bar. And so we get y bar over LF to the n is equal to 1 over KD to the n, 1 over KD to the n, minus y bar over KD to the n. And what that means is that if we plot y bar over LF to the n, we should get a straight line with a slope of negative 1 over KD to the n. I'm sorry, if we plot y bar over LF to the n versus y bar, again, a parameter proportional to bound receptor. Y bar is proportional to bound receptor. We plot something proportional to bound receptor divided by the free ligand to the nth power against the bound receptor. Again, not an intuitively obvious coordinate system, but it gives us a very simple mathematical relationship where you have a linear equation. The slope of this parameter relative to y bar is just negative 1 over KD to the n, and the intercept at y bar over 0 is 1 over KD to the n. Now, if you're trying to investigate and understand whether the reaction is cooperative, of course you do not know yet know n, and this is not, frankly, a good way to determine n, but what we're going to do is we're going to see what happens when n equals 1. So when n equals 1, this then becomes y bar over LF to the n, and over here we get 1 over KD minus 1 over KD times y bar. So this is a very, very simple equation. Again, sort of a weird coordinate system, but it's a straight line. Y bar, or bound receptor over free ligand, plotted against y bar, or something proportional to bound receptor, is a straight line with slope of negative 1 over KD, and with an intercept at y bar equals 0 of 1 over KD. So the intercept over here gives you 1 over KD. Of course, there are many other ways for us to get that. The slope of this line is similarly also 1 over KD. But the important point here is that the fact that it's a line means that this is an independent site binding. And again, this is a very sensitive way to detect cooperativity, and therefore the linearity of this is a really excellent way to verify that there's independent site binding. That's why people put a Scatchard plot in a paper. If they're putting in a Hill plot, they're probably trying to show the degree of cooperativity. They would put in a Scatchard plot to show that the binding is non-cooperative, right? So again, the mathematics, because of the n in the denominator here, are much more complicated. This is no longer a particularly, well, if you're plotting just y bar over LF to the first power, has a very complicated relationship towards y bar over LF to the nth power. So basically, we're just going to entirely ignore that. Again, the whole point of this is to say, basically, does n equal 1? If n equals 1, it's a straight line. Well, what do you get if n is not equal to 1? And why is this such a sensitive way to look at cooperativity, to detect cooperativity? That is explained over here. If you think about what we're plotting, y bar over LF, well, now let's go back to our normal coordinate system, y bar on the vertical axis, LF on the horizontal axis. What is y bar over LF? Well, y bar over LF is the slope of the line from the origin to a given point in the binding curve, right? So again, what is y bar over LF? This is y bar over LF on the vertical axis. If we have the binding curve plotted in a normal format, y bar at this point over LF is basically the ratio of this value to that value. That is the slope of the line from the origin to that point. The math we just did a few minutes ago tells you that the blue curve, which is a non-cooperative binding, when we replot the data in the blue curve in this seemingly funky format, what this math tells you is that this blue hyperbolic independent site binding curve corresponds to an exactly straight line in this weird Scatchard plotting format. Well, what happens if we have cooperativity? So let's consider the n equal 4 case. What happens is that the slope of that line to a given point on the binding curve is now initially much lower than the slope of the independent site binding curve, right? let's come down over here. When we get to y bar equals 0.5, all of these curves, irrespective of cooperativity, at LF equals KD, in this case in these plots KD happens to be 2, when LF equals KD, we are of course always at the 50% saturation point irrespective of cooperativity. That means for irrespective of cooperativity, y bar over LF at the 50% saturation point is always at the same point in all of these curves. So all of these curves should intersect, right? So y bar over LF is the same irrespective of cooperativity at the midpoint of fractional saturation, and we see that down here. But coming back up here, again, for the math summarized over here shows you that the independent site blue curve gives you exactly a straight line. The question is, how do the cooperative curves compare? Well, the cooperative curves, the slope at every point, the slope from the origin to the point on the binding curve, right? Y bar over LF, the slope from the origin to the point on the binding curve, is now much lower. And the more cooperative it is, the lower it is, until you get to the midpoint where everything meets. Above the midpoint, it's much higher, right? Basically, you have lower slope in the binding curve until the midpoint, and then higher slope after the midpoint. That's true if we look locally. It's also true if we look at the slope from the origin at any given point, right? Starts off low, starts off much lower in fractional saturation than the independent site binding, goes much higher. So what that means is that when we now look at this in the scattered format, because the slope from the origin to the point on the binding curve, when we look at, right, y bar over LF, slope from origin to the point on the binding curve in the normal binding format, this is going to be lower than the value for the independent site binding if it's cooperative, right? These values are very much lower. When we get above the 50% saturation point, they will be higher, right? And so lower slope, right? We're looking at the slope, y bar over LF, the slope from the origin, right, to a given point on the fractional saturation curve. Y bar over LF, slope from origin to this point. For a cooperative binding, that slope is lower until you get to the midpoint. It's lower until you get to the midpoint compared to the independent site binding given by the blue curve. It's higher when you go beyond the midpoint compared to the independent site binding curve. So basically, what is this looking at? This is looking at the curvature of the binding plot. So it's a very sensitive way to evaluate that curvature. You need to do a little bit of algebra to show that this funky scattered plotting format gives a straight line when n equals 1, but the algebra is pretty straightforward. It proves that for n equals 1, for an independent site binding, this is a straight line. Compared to that straight line, we can see that the scattered plot measures essentially the curvature, the more shallow curvature of the cooperative binding compared to the independent site binding before the midpoint, and then the steeper curvature of the cooperative plots compared to the independent plot after the midpoint. Okay, and so that summarizes both the math and the utility and a sort of conceptual or qualitative analysis of why the scattered plot works. Again, this limitation involved in using the scattered plot is that you need to know the free ligand concentration. The next point I'll make may not be obvious from what's plotted here, but the fact is that this works just as well. In this case, for the Hill plot, we actually need an estimate of fractional saturation point because we're plotting basically free over bound. So we only know the free to bound ratio when we know where saturation is. If you think about it and look at the math up here, this will work equally well if we just plot bound receptor concentration over free ligand concentration. For the scattered plot, we actually don't have to know the saturation point so well. It is an advantage of it. We do need to know the free ligand, just as we did for the Hill plot, and so that is a limitation of it. But it is, again, an incredibly sensitive way to detect cooperativity, and that means it's a very rigorous way to establish that there is no cooperativity or independent site binding. If you see a scattered plot in a paper, it is there to make the point that it is a linear dependency. It's very rare for anyone to show this unless it is linear, and they're doing that to make the point that the binding is independent site binding. Okay. And so this just fleshes out everything we just talked about. The slope of the line from the origin to a point on the fractional saturation curve is basically what's plotted in a scatter plot. It is, if it's linear, it's non-cooperative. If it's cooperative, it is a very sensitive way to measure the curvature relative to the independent site binding curve. Okay, so the next thing that we, in final part of topic in this presentation is an examination of what logarithmic binding plots are about. A logarithmic binding plot, that term is typically used to refer to a plotting of your data of y bar rather than against just the free ligand, against the logarithm of free ligand. And the whole point of the logarithmic binding plot is that it enables data with disparate KD values to be plotted on the same graph. I'll come back to that at the end. So we're going to start with a normal set of with the binding curves plotted in what we've in the same format we've used till now. We'll start with a plot of y bar over free ligand. Again, this is the normal way we plotted the data to mostly to this point in time. In the course, we plotted data in this format or something like this format. Again, this is, however, a free ligand plot, so that is important to bear in mind. So here are shown basically 8 simulated binding curves for different KD values, KD 2, 10, 50, and 250, and cooperativity either 1 or 2. Of course, with the same KD, the curves that have the same KD, they intersect at the 50% saturation point, of course, when LF is equal to KD. And as the KD goes up, the midpoint of these graphs goes out further and further. So you can see here we get a very good sort of display on this linear axis of the binding curve for the receptor ligand interaction with KD of 10. The data for KD equals 2 gets rather compressed. The data for KD equals 50 is visible and sort of interpretable. We're nowhere near saturation, and the data for the KD of 250 is almost effectively uninterpretable. Now, between 2 and 250, there's a little bit over a 200-fold difference in affinity. I'm sorry, a little bit over a 100-fold difference in affinity. That's a large but not astronomical affinity difference. In fact, it's very easy when you make mutations in your favorite receptor to come up with affinity differences this large. In the course of drug discovery projects, you will very commonly, typically, encounter differences in affinities between different ligands, between different hormones that differ by 100%. And if you want to analyze all of these things as part of the same, sort of conceptual analysis, it would be nice to get them on the same graph. And you can see here that in the linear plotting format, the 100-fold difference in affinity constant makes it almost impossible to see all the data on the same graph. So to consider what happens now, first of all, consider what we're going to observe when we convert this to where we're going now eventually is to convert this axis to a logarithmic axis, right? So we're going to take every point here, given free ligand value, we're going to take its logarithm, we're going to replot with logarithm on this axis. So you've all probably seen things like this before. It can be a little bit confusing, but I'm going to step you through the details in a way that shows you how to interpret the logarithmic binding curves, what effect the dissociation constant and the cooperativity have on what you're going to see when you redo this in a logarithmic binding format. So the starting point for that is to write the equation that we looked at before, the standard equation for fractional saturation versus free ligand for a cooperative binding reaction that has a KD of KD to the n in has an affinity constant of KD and a cooperativity of n. So that is, of course, y bar equals LF to the n over KD to the n plus LF to the n. The first thing we're going to do is to normalize these curves individually to its specific KD, right? So we're going to divide through the top and the bottom by KD to the n. So we've basically done this before when we discussed the point that the KD is a metric or sort of a universal normalizing factor for binding curves. And once we normalize to KD, all binding curves look the same. So this point was actually treated earlier in the PowerPoint stack, but it was not sort of shown exactly the same graphical way for quite as many data sets, but you have seen the basic point here before, right? So mathematically, once we normalize to KD, we get y bar equals and now I'm not going to write alpha. I'm going to say alpha, this variable alpha equals LF over KD to the n. So once we divide through by KD to the n, we would get LF to the n over KD to the n, or
it's
alpha
1
to
o'clock.
the n. Divided by KD to the n over KD to the n, of course, is 1. And this is, once again, alpha to the n. So when we divide through this standard equation by KD to the n, we get alpha to the n over 1 over plus alpha to the n, where alpha is defined as LF over KD. Basically, the free ligand normalized to dissociation constant, which we have looked at before when considering making the point that the KD is the metric for binding interactions. So these curves, of course, now, once you normalize to KD, the free ligand 50% saturation will equal KD, so that means alpha will equal 1, right? Free ligand equals KD at the 50% fractional saturation point, so that's what we see here. The cooperative binding curve now shows the sigmoidicity, or curvature, typical of a twofold cooperative binding, and the independent site binding is hyperbolic. So we still see the shape difference, the characteristic shape difference between the n equals 1 independent site binding and the cooperative binding. Independent site binding in here, and cooperative binding, of course, is the independent curve, the cooperative curve. If we plotted curves with a higher degree of cooperativity, we would see, something more steeply sigmoidal, just like we've seen before in other slides. But now, by normalizing to KD, we have sort of collapsed all curves with a given degree of cooperativity immediately on top of one another. We still see differences in shape, in functional form, for curves with different degrees of cooperativity, but once we normalize to KD, the the shape of the curve depends only on the cooperativity. So we have been through this before earlier on. Now what we're going to do is we're going to do a logarithmic transformation of the horizontal axis, right? The y-bar axis is going to stay the same. Any point here is going to be at the same point over here. But what we're going to do is basically we're going to stretch these points out in a certain way. Actually, we're going to compress the points up here and stress the points out down there by taking the logarithm of this variable alpha, which is equal to LF over KD. So if we consider what the logarithmic function looks like at alpha equals 1, of course log of 1 is 0. As you go up from 0, logarithm increases monotonically. Monotonically means go up in alpha, go up in log alpha. This is a monotonic function. It's a monotonic function throughout its range. And the range of the logarithm is 0. Note it's actually greater than 0, so you cannot actually calculate the logarithm when the concentration is exactly 0. But the range is anything greater than 0 to whatever, infinity. And that logarithmic function is monotonic all the way through its range. And so what that means is monotonic. It means that a point to a lower value in alpha will mean a lower value in log alpha, right? Lower values in alpha, right, as we go down here, lower values in alpha go to lower values in log alpha. Higher values in alpha go to higher values in log alpha. That's what it means to be a monotonic function. But what this does, it effectively compresses the data up. It compresses it effectively, right? If we look at alpha at 150, right? So we look at alpha at, whatever here, 10, 50, 100, 150. What it does is it sort of compresses the data at higher values of alpha to be closer to one another in log alpha. In contrast, below alpha equals 1, it actually expands it out, right? So what has happened? So if we use this alpha equals 1, or LF over KD equals 1 point for reference, right, which is 50% saturation, 50% saturation. What happens is we basically compress all the data from these higher points in the alpha coordinate, and we expand the data, right? We take the data in here on this graph, and we expand it out to when we go to the log alpha axis, right? So we do a transformation of the horizontal axis here, which compresses the points at higher alpha and expands the points at lower alpha. So this expansion at lower alpha means that even the non-cooperative case, which is sort of this purpley hyperbolic curve over here, because of the expansion of low alpha of log alpha compared to alpha, when alpha is less than 1, so we will get an expansion of the curve below alpha equals 1, and that expansion will basically make the independent site curve look sigmoidal. So that's a critical point. When we expand when we transform in log alpha, we expand the data points below the 50% saturation point. That expansion stretches these things out and gives the independent site binding curve the sigmoidal appearance. Now, of course, we haven't changed the y values. So wherever the cooperative curve is above the independent site curve, that's going to be the same once we do this transformation, right? So below the 50% saturation point, the cooperative curve is below the independent site curve. We haven't changed that. The cooperative curve is always below the independent site binding curve, below 50% saturation. And it's always above the independent site curve, above 50% saturation. So the steepness, the relative steepness of these curves is unchanged. Independent site binding is hyperbolic, two-fold cooperativity steeper, four-fold cooperativity would be yet steeper. If we had full four-fold cooperativity here, it would be yet steeper. We have not changed the relative steepness of this. But what we have done is made the independent site curve look sigmoidal while retaining the relative steepness. Now, why have we done this? Well, we've done this because we've taken data points, like let's say for the KD equals 250 curve, we need data points like up to LF of 1,000 really to get a good solid binding curve. The logarithmic transformation has taken those points that would be, sort of usually over here and compressed them down so that we can see them on the graph. And it has, in the meantime, also expanded the points below 50% saturation so we can see those data more clearly in the graph. Okay, so now what we have is a plot of y bar versus alpha. Yes, and so a point about the axis titling. So what we've plotted is y bar versus log alpha, right? We've done the logarithmic transformation. But caveat emptor, this says alpha equals LF over KD. And why is that? Well, because the numbers we're showing here are in LF over KD. This axis has a logarithmic scale, but the numbers I placed on the, and you can see the logarithmic scale like from the irregularity of the ticks, right? These ticks are getting more and more compressed because this is a logarithmic scale. But the numbers I've put here, rather than putting in the number with, log alpha is 0, right? So I haven't put log alpha on the axis. Instead, I have actually put alpha. So this is alpha 1, alpha 0.1, alpha 10, alpha 100, alpha 1000. Because the numbers are actually alpha values, not log alpha values, the axis is labeled, right? The axis is labeled alpha equals LX over KD because that's what these numbers are. But the scale is logarithmic, so that can be confusing, but that is the way that people will typically publish this in journal articles. So now we have a plot in log alpha. What we want to do, however, is get to a plot in log LF. Well, what do we do to do that? Well, now we just have to figure out how log LF rates to log alpha. If alpha equals LF over KD, log alpha, I'm sorry that this says A, but I will fix that. Log alpha would be log LF minus log KD. That means log LF equals log alpha plus log KD. Right? And so to go from log alpha's coordinates to log LF coordinates, we need to take the graph in the log alpha coordinate and add to it log KD. Now, because each of the curves here was normalized by its own specific KD, that means for every curve here where they're superimposed, to do the transformation back to the LF coordinate system, or now log LF coordinate system, we need to use the KD specific for that binding curve. And when we do that, we spread these things out according to their KD. Right? If the KD is 250, log KD is higher, we get more of a displacement when we do this transformation back to the log LF space. If KD is 2, we get a much smaller displacement. So when we do this final step, we now spread out. Guess what? We spread out the midpoint of the fractional saturation curve according to the KD, because, of course, if we're now plotting in LF, the value of LF at the midpoint of fractional saturation has to be KD. When the KD values for the curves are different, therefore the midpoint will be at different points, and so this does all make sense. If we look at the 50% saturation point, now that we're back in basically log LF, we can go down here and we can find log KD for this curve. Log K, right? This would be log 2. This would be log 10. This would be log 50. This would be log 250. Once again, the axis is logarithmic in scale, but the numbers are not numbers of log LF. their numbers of the numbers are just LF. The scale is logarithmic, but the numbers that we're putting here, the labels, are the actual LFs. So this is LF in micromolar, 1 micromolar, 0.1 micromolar, 10 micromolar, 100 micromolar. So we label the axis as LF because the numbers are in LF, even though the scale is not a linear scale and is instead a logarithmic scale. Again, you need to sort of just think about that, focus on it. It can be a little bit confusing, but I've plotted this here specifically because when people make plots in a journal article in this format, 95% or 99% of them will be labeled in LF rather than log LF. But nonetheless, it's a logarithmic axis. That means even the independent site binding curves, right, the darker red, blue, green, magenta curves, purple curves, the darker curves are independent site binding. When we go to logarithmic format, they're stretched out so that they look sigmoidal, right? So in the logarithmic binding plot, even independent sites look sigmoidal. But as the cooperativity increases, they become more sigmoidal, and still the degree of cooperativity scales, the degree of sigmoidicity scales with the cooperativity. Less cooperative, less sigmoidal, independent site, the least sigmoidal. Again, we haven't rescaled this axis, so if the cooperative curve, where the cooperative curve is above the independent site curve over here, it will be above it over here. Where it's below, it will be below. If it's below over here, it will be low over here. As we go to higher cooperativity, it will get even lower below the 50% saturation point, higher above the 50% saturation point, right? And therefore, we will. If we had more cooperative binding interaction, if we had n equals 4, it would be even steeper and more sigmoidal. So the degree of sigmoidicity still is monotonically related or increasing consistently with the cooperativity. The least cooperative independent site binding is the least sigmoidal. The most cooperative or most independent site, the most cooperative binding will be the most sigmoidal. More sigmoidicity, steeper slope, more cooperativity. That relationship still holds, but even the independent site binding curve is cooperative. Okay, at the 50% saturation point, of course, LF is equal to KD. So if we go down here, we get the KD, right? So with the numbering of this scale, that's 2. The KD is 2. The numbering here, the KD is 10. The numbering here, if we count the ticks, the KD is 50. The numbering here, we'd see it's roughly 250. Right? And so, of course, LF at 50% saturation is always KD. So we come down here to the LF axis, we get KD. Because we've labeled it in LF, we can actually directly read off the KD. But remembering, this is actually scaled as log KD. And so, this is basically a log KD axis, but labeled log LF axis, but labeled in LF. And that means the labels, when we come down here, although the plot is logarithmic, the shape of the scaling of the axis is logarithmic. The labels are given you directly KD. So I think if you just now circle back and simply compare what you see in this curve to what you see over here, right? We've lost the KD250 data on this plot. We can barely see the KD2 data. It's all compressed towards the origin. We can now see all the data very easily, even with a 2 order of magnitude affinity difference. But again, in many experimental situations, you'll have even a greater affinity difference. So that's really the utility of logarithmic binding curves. It can take data with very different KDs on very different scales relative to LF, and put them all in a single coherent plot on one graph where you can see all the data, both at saturation, at very high fractional saturation, very low saturation, everything with very different KDs. You can just all get them nicely displayed together. The 50% saturation point, of course, gives you KD or log KD. That will not change. The biggest difference is that the independent site binding is sigmoidal in this plotting format, but it is still true that more cooperativity gives steeper graphs and more sigmoidicity. Okay, and so that covers a bunch of things that are important because the 3 plots that we just went through, the logarithmic binding curve, the logarithmic binding plot, the scattered plot, and the Hill plot, you will see them in published papers with great frequency. And therefore, it's worth knowing what they're all about.